In this lesson, we're going to talk about something called similarity transformations. And we're going to start off by looking at this image and a pre-image. Define the transformations that would map the pre-image on the left to the image on the right. And if you compare the two, if you're a ruler, you could measure sides, or if you have a compass, you could measure sides. You'll see that they are the same size. So what I could do to map one to the other is basically a translation. If I call this A and B, it would be a translation of vector AB. What do we know about the figures? Well, since I only used a rigid motion to map one to the other, that means they are congruent. We know that. That's kind of review for us. So now let's look at these two, the pre-image and its image. Now they're not the same size. So if we want to define a transformation that maps one to the other, we're first going to have to probably dilate it. Now, depending on how these things line up, it's possible that we don't have to translate it all. If we find the center of dilation, it's quite possible that this is one step. I don't have my ruler with me. You can measure that, but I do believe that this is a scale factor of 1/2, so we could dilate it down to 1/2, and I believe that's the only thing we would have to do. What do we know about the figures? Well, we know dilations create similar figures, so they are similar. Not congruent, but similar. So this brings us to what we call a similarity transformation. So we're going to define what that is. We've had congruent transformations using only rigid motion, so if you think about it, a similarity transformation would probably also involve a dilation. So here's how we define a similarity transformation. It's a series of rigid motions and a dilation, so that's the new thing. We can dilate now. That's going to map a pre-image to an image, and those two images are going to be similar, not congruent, but they're going to be similar to each other. So if I wanted to draw an example of this, I could start with a square. Let's just put a little right angle in there, and I can create a bigger square. That's something to think about. Are all squares similar to each other? We'll have to talk about that. So the angles are congruent, which would make the squares similar to each other, actually. So all squares are going to be similar because all of them have 90-degree angles, and that doesn't change. So I can carry this square, I can rotate it, and then dilate it, and it would map to the other square. So if we're going to define what similar is, basically there are two parts to being similar. If you remember, the angles are congruent, and the sides are in proportion. So when I take the ratio of each side, you get the same fraction, the ratio of corresponding sides, proportion. Okay. Again, think of an equilateral triangle, or any triangle actually. It doesn't have to be equilateral. If they're similar, that means corresponding angles are going to be congruent, and corresponding sides are going to be, their ratio is going to be equal. So in this case, I would say that A over B is going to be equal to C over D. That's what it means to have similar shapes. So just like we described transformations of rigid motions to map one image to pre-image to its image, we can do the same thing with similarity transformations. If I look at figure A prime, it's similar to figure A. So we want to talk about what transformations would map A to A prime. Well, I'm decreasing in size, so that's going to be a dilation with a scale factor less than 1, and then I'm also rotating it. So if I write this out, I could say, let's say my scale factor is 1/2, and then I'm also rotating that about a center point, let's call that C for center, all of it looks like 180 degrees. So I'm rotating it about itself 180 degrees, and I dilate it by 1/2. The next one, if you look, is there a sequence of dilations and basic rigid motions that takes the small figure to the large one? Well, it's kind of an optical illusion. You can see the heads are different sizes, but the bodies are actually the same size. So that's going to be no, because corresponding lengths are not in proportion. So this is what I would say. No, they are not. There's no sequence of dilations of basic rigid motions that carries the small figure to the large one, because not all corresponding lengths are in proportion. The heads change size, but the bodies don't. So we can also evaluate things by putting them on the coordinate plane. Given the coordinate plane shown, identify a similarity transformation if one exists, mapping x onto y. And if one does not exist, explain why. So if we look at these two images, I want to map x to y. If you evaluate the slopes of each of these lines, or the lengths, you will see that each one is cut in half. So if I'm going to map x to y, there are two things that's going on. First, we can reflect over this line. So it's a reflection over the line x is equal to 11. And then we're going to shrink down x, a dilation by a factor of 1/2. You'll see corresponding angles are congruent and corresponding sides are in proportion. They all have the same ratio of 1 to 2. So here's an example that could also be kind of an illusion if you're not careful. It looks like these things are dilated because I can connect points back to a single point. But look at the angles. Angle DAB and over here, they're not the same. So since the angles are not the same, this definitely is not a similarity transformation, because the angles all have to be congruent. Corresponding angles have to be congruent if you're going to have a similarity transformation. So no, angles are not congruent. And we will, in class, we're going to look at using our compass and constructions to create similarity transformations.